Hello everyone, so Sanrup here, and today I'm going to be starting on with a simple tutorial on how to implement rigid body based FPS controller in Unity. So let's just start with a quick demo. So over here we have a controller, so as you can see the controller is moving around in the scene, it can push blocks, interact with the physics. As you can see this block is quite light and it's able to push it, while the heavier blocks it's a bit difficult to push. So over there we have seen a few of the physics interactions. Now we can see how the player sort of interacts with stairs, how it's able to climb them quite smoothly. It even works on ramps. It doesn't slide off a ramp, it stays there. Even on the stairs, it holds its position. It can also jump across platforms, jump on it, doesn't fly off the slopes, sticks to the ground quite well. So yeah, these are like sort of some of the features summarizing it. So yeah, so I guess just a good quick intro. So sort of let's just start with how this is sort of implemented. And so before we start with scripting the controller, I just wanted to show the setup of our player. So our player is just basically a sphere with a rigid body attached. So the few things that I've configured here is that I've frozen the rotations, meaning the player will not rotate in the X, Y or the Z axes. Along with that, the positions for the X and Z directions are frozen. So this is just a temporary thing. We'll be later be enabling them. So you can ignore that. Other thing is we have a sphere collider setup. So the sphere collider has a physics material layer attached to it. So the reason why this is done is so as to set the friction to 0. So key thing to remember is that this setting friction combine is set to minimum. So that basically ensures that the player sort of does not stick to the walls or stick to any surface. So minimum just basically says that use the minimum value of the friction coefficient. So let's just play. So thing you notice is that the player is directly stuck to the ground and doesn't really do much. So the special thing is how do we sort of get it to interact with all the stairs and the ramp? So the thing is this player in the controller is actually not stuck to the ground but is sort of slightly levitating in the air. So why is that important? So here see if I even if I just move the player forward because of the levitating behavior, it's sort of able to take the steps and it directly moves up. If you throw it down a ramp, it detects the ramp, it detects the floor and pulls it down. So that way it's sort of able to balance itself on the ramp. So this is really interesting because you can get it to work on any complicated surface. Like let's have a look at this curved stair. So even on this, because of the levitating behavior, the player just has to move forward and basically the spring script sort of handles everything. So as you can see, it's quite easy for the player to step up the stairs. It just has to move forward, go up the edge, the spring pushes it up and it moves up the step. So this is sort of handled by this spring hover script. So before scripting the entire controller, we'll sort of implement this behavior, then we'll start extending it and add the arrow keys control and sort of complete our controller. So let's just start implementing the behavior of the spring. So before we sort of start implementing, we'll need a few parameters about the player, like the player height, like the height at which it should be floating, public float player slack height, which is just basically a margin of error that it's given, so it can sort of hover above that, meaning a slight error from the ideal height. Then is the radius of the player, which will be using in raycasting. I'll explain what raycasting is and sort of how we are using it in our case. So this seems to be it. So let's just sort of understand what raycasting is. Okay. So that quick intro. So let's just sort of again maintain a few parameters that sort of the recast we're using and that we want to store. So the first is the hit point. The other is a boolean that tells us if we are on the ground. And yeah, I guess that's about it. So since we are dealing with physics, we want to do all our updating code in the physics update. And in the physics update, we'll call a function called handle grounding, which will do the recasting, check if you're on the ground and find the point at which the recast hits the ground. So let's just understand what recasting does. So let's say we have a sphere that represents a player, and this is the center of the player, and let's say we have a floor at the bottom of it. So for recasting, you can just imagine a line pointing in the downward direction. So basically, recasting sends sort of like an imaginary sphere along the line. So the sphere goes moving down the line, and let's say if it collides with something, so let's say it collides with the floor. So once it collides, it sort of tells you the hit position, the object it collided with, and basically gives you information about the point at which the collision happens. So recasting, just to summarize it, here is just basically shooting an imaginary sphere downwards and sort of finding where the collision happens to sort of find if the player is grounded or not. So what we are going to be doing is this ray, which I've shown here, will basically be as long as the player height plus the slack length. So the slack length just gives a little margin of error. So even if the player is just slightly above the ground, you don't want to really off ground the player. You sort of want it to see it's still on the ground. So this is just sort of like a small value. It sort of just adds a margin of error to it. So basically what happens, a downward ray of this length is shot, over which a sphere is basically traveling, and if it finds any collision, we just say that the sphere is grounded, and then we'll later be sort of be using this hit point to compute the spring forces. So let's just hop back to the code and see how this recasting is being implemented and used. So as I've explained, so just start with the quick setup. So one more thing about the recasting is you have to specify sort of like the mask over which you are doing the recasting, meaning the layer of the colliders that are going to be there and sort of going to be interacting with that imaginary sphere. So oops, layer mask is equal to layer mask dot get mask. So we are going to be using a custom mask called floor. I'll let us show you guys how you sort of implement and sort of add that mask. So for now, you can type that in the code. And we'll have one more variable, which is just recast hit, which will basically store the results of our recast. So let's just invoke the recast. So we physics dot sphere cast, since we're going to use sphere cast, there's also a capsule cast, recast, which just shoots a single ray, but since we are shooting in sphere, it's called a sphere cast. So the way you call it is first you specify the origin or the starting point of the ray, then you specify the radius of the imaginary sphere, and then you specify the direction where you want to shoot the ray, then you specify the variable where the results should be stored. Do keep a note of the out variable, which sort of tells us that the result should be stored. And then you want to mention the height of the ray, so this is just the player height plus the small margin of error that we are giving it, and then the mask along which you want to do a recast. So the reason why I've implemented a mask here is basically we do not want the imaginary sphere to collide with the player's collider and sort of affect the rounding results. Because if that happens, that will never be able to detect the ground and it will just collide with the player's collider and it will cause issues. So masking basically avoids that. So that's why we are using mask. So with this, we know if the player is grounded or not. So let's just calculate the hit point. If it's on the ground, so if it's on the ground, the hit point is just going to be recast hit dot point. So this code just simply allows you to check if the player is on the ground, and if it's on the ground, it takes the hit point, which will be later used for calculating the spring force. So before we start with understanding how the spring force is implemented, let's just have a look at how the spring forces sort of work. So just a quick video about it. Okay, so since we now understand how spring forces work, we'll just implement them. So the way you want to implement them is going to be happening in the handle string. So before we do that, we just want to set up a few things. So we want to configure the springs. So how do we do that? So the first thing is we want to have the two constants, public float spring force constant, which is basically the force that the spring applies. Then the spring damping constant, which is the constant for the damping force. And now, since we are going to be applying forces, we'll need a reference to our rigid body. So let's just get the reference and assign it. So like I've said, there's sort of like a spring mechanism between the player and the floor. So let's just consider this imaginary spring that is connected to the center of the player and the other end is connected to the floor. So what happens is, like a spring, if you pull the player up, meaning the player is above the resting height, it gets pulled down by the force, and vice versa. If it's pushed down, then it gets pulled up by the spring. So how does the spring force work and how do we calculate it? So let's say we have a spring whose resting length is L. So if you pull the spring forward, you know that there's a force that acts in the direction that's opposite of this displacement, meaning there will be a force that will sort of pull it backwards. And similarly, if you compress the spring, there will be a force that pulls it forward. So there's a law called the Hooke's law, which basically tells us that the force is equal to the negative of a constant multiplied by the change in length. So this force basically acts in the direction opposite of the displacement. So the thing with this force is it sort of has a tendency to get the spring to be centered or at the resting length, meaning even if you slightly displace the spring from its resting position, the force pulls it back to the resting position. But the problem with this force is that it does not deal with the velocity. So what happens is your player will sort of keep oscillating up, down, up, down, up, down on the resting position. So to check this behavior out, we'll be seeing it later in Unity to get a more clear understanding. But yeah, the basic issue is the player keeps oscillating like this. So you want to fix that. So solution to that is to use a damping force. A damping force is basically a force that opposes velocity. So it's basically a force that's given by a constant into velocity minus kV, meaning it acts in the direction of the opposite of the velocity and sort of kills the velocity. So what happens is your oscillatory behavior, velocity will slowly be killed and your player will sort of be stable. So using the two forces, we have a setup where there's a spring and it's stable above the floor and sort of locked over there. So whenever you push it down, upward force will be there, which will bring it back to the equilibrium. At the same time, the damping force will create a small downward force which will sort of reduce the velocity to zero and the player will sort of lock its place above the floor. So if you do not understand, it's completely fine. We'll just have a look in Unity and sort of tune the parameters, and then you'll sort of get an understanding of the two forces and how they sort of come into the picture. Okay, so our setup is done. Now let's start calculating. So if we are grounded, then first we're going to get the spring length, the distance of the player from the ground, which is just going to be vector 3 dot transform dot position. So the distance from the center to the head point, and since we want to want it along the downward direction, since we want it on the vertical direction, we are going to be using vector 3 dot up. So this basically calculates the ground distance. Now we want to calculate the delta distance For the Hooke's law, which is equivalent to the ground distance minus the player height, which is the resting length of the spring or the resting position that we want. And using this, we can compute the spring force, which is just going to be vector 3 dot up. The minus sign comes from the Hooke's law, so I'm using vector 3 dot up just to sort of show that the minus sign is there, and so it's easy to understand. The delta distance and the spring force constant. So we have the spring force calculated. Similarly, for the damping force, it's again quite simple. So we just want to project our velocity in the upward direction. We're taking a negative sign because we want to say that you want to move in the direction opposite of the velocity, and then we'll just multiply it by the spring damping constant. So we compute the final force, which is basically the spring force plus the damping force, and then we use our reference to the rigid body. Then we add the force, final force, and we're done. So let's just head back to Unity and let's try tuning the parameters and see how our spring works. So yeah, so let's just start with applying this behavior to our new player, the spring hovering effect. So we want to set the height of the player, so I'm just going to set it to 1 meter, slack length of around 0.5, the radius of 0.49. So I'm not setting it to 0.5 exactly because of the way this physics spearcast works. So the issue is if a collision happens at the start, then it basically ignores it. So if you set it to a radius that's slightly smaller, then you can sort of ensure that a collision never happens at the start of the ray because it will have to move slightly ahead to sort of collide with the floor, and therefore you can get the hit point and sort of detect the results in spearcast. So we just set the radius to be slightly smaller than the actual radius, which is 0.5. And let's just start and sort of see how you tune this. So for tuning, you'll sort of want to start with the force constants. You'll want to start bumping it up slowly. You want to notice when the player sort of starts hovering. So you can see it starts hovering at around 400, but it's not strong enough. So this was just based on tuning, and I found 1000 to be strong enough to push it up in all cases. So when I set that to 1000, now you'll notice the bumping or the oscillating effect of the player. This is because our damping force is not enabled yet. So if you just go ahead and enable the damping force, you'll see the player becomes stable. Now you can see we have the hovering effect that I had mentioned in the start. So see the player hovers quite well, can go up and down, sticks to the ground, and we have completed. So before moving on to the next part, just a quick intuition on how do you want to tune these values. So first, don't think about that damping, just tune the force constants until you see the player is sort of able to maintain the position, and then start bumping the damping up slowly until the player sort of gets stable. So as you can see, I've tuned it for 500 and you can see it does work quite well, but the thing here will be is that the force won't be strong enough. Oops, the player fell down. So right now the tuning won't be that significant, but later when we sort of start moving the player, you'll notice the effect of how strong the force is, because this force sort of also gives the downward force which prevents the player from like flying off ramps or flying off stairs. So we'll just later understand what role these two forces play. So for now, you just want to have a player that sort of hovers in sort of like a stable way, meaning if you pull it up, it falls and sort of stays at its resting position. So one more thing is it's possible that the resting height is not exactly the one that you have set because even gravity is also acting on the player. So way to address this is sort of you can start bumping spring constant and you'll see the y sort of starts going near the player height. I mean, as much as you increase or more closer it will become, but at the same time it becomes more unstable. So it's completely fine if it's slightly of the height. You just have to sort of account that in your calculations. And yeah, so let's just start with the second part where we trying to move around our player. Since now we have implemented the hovering effect of the player, we now want to sort of implement the motion or the movement of the player. So a few things that are there in the movement of the player. Config is basically the movement speed, the maximum acceleration that the player should be applied on. And one more thing for our calculations is basically the hit normal. So the hit normal is basically the normal of the plane on which the player is currently standing on. So we are able to apply the forces properly so that the player moves correctly on the plane it's standing on. So let's just see how we will implement that. So first we want to get the current normal of the plane, which is quite simple as the result is just stored in the recast. But in the case if you're in air, so you want your normal to be vector 3 dot up. So you can also have some motion in the air. And for the ground, it's just going to be the normal of the plane you're standing on. So with that being done, so to calculate the direction of motion, we first need to take input from the keyboard and then calculate the desired movement direction. So a good practice in Unity is to use the update function for fetching player input instead of directly fetching the input and fixed update and performing the computation. So for that, we'll be using the update event to fetch the player input. So for player input, we'll need to introduce an additional field in the class, which is input direction. It's a vector 3. So we'll just initialize it and assign values to it. So it will be taking the two input axes, which are the horizontal axes, meaning your sideways axes, the vertical axes, and 0 for the other axis. Now we will want to clamp this. So the reason for clamping this is, let's say if you're moving diagonally, meaning you hit both the front arrow key and the right arrow key, then what will happen is it will result in moving one unit in the forward and one unit in the right direction. This gives an additional velocity or extra velocity when moving in the diagonal direction. So what happens is this gives a bad effect that the player moves very fast in the diagonal directions but moves slower in the orthogonal directions. So to fix this, we basically clamp the input direction vector to 1. So in case if that ever happens, the vector just gets scaled down to 1 and therefore it moves at a constant speed or less than 1 in all the directions based on the input that we provide. So this gives a slightly better effect to the control and sort of limits that speed illusion where it starts moving very fast, that speed effect where it starts moving very fast in the diagonal direction. So let's just implement the code for our movement. So we'll call that handle motion. So handle motion. So the controller before it starts moving is first needs to calculate the desired velocity. So the desired velocity is going to be the input direction dot x into transform dot right input direction dot y into transform dot forward, and we scale it up with the movement speed. So once we do that, now we want to project it on the plane that you're going to be moving on. So this is just simply done using vector 3 dot project on plane, desired velocity, and hit normal. Similarly, we want to do the same for current velocity. We'll later explain why we are using the current velocity. It's going to be vector 3 dot project on plane. So to get the current velocity, you can directly fetch it from the rigid body, which is just rigid body dot velocity. We project it on the plane. And yeah, so now what do you want to do is you want to calculate the delta velocity. So delta velocity is a velocity that we need to move in the desired velocity from the current velocity. So this is just simply subtracting it. So now why are we doing this? So since the controller does not directly apply the velocity but rather applies a force, therefore we need to calculate the force such that it moves in the desired velocity. So force is nothing but mass into acceleration, and acceleration is nothing but rate of change of velocity over time. So basically what do? We calculate the delta velocity, then calculate the rate of change of velocity over time, which is just delta velocity divided by the physics time step, means the physics delta time. And we have the acceleration, and then we can directly calculate the force and apply it. So this allows us the controller to sort of apply a force in the desired direction and make the player move in the desired velocity. So how do we calculate the acceleration? So the acceleration is just basically delta velocity divided by time, fixed delta time. Now we want to do one more thing on this acceleration. We cannot directly apply this acceleration because it's possible that this acceleration will be too large. So basically, if there's some heavy obstacle standing in front of the player will just apply an infinite amount of force and just push away and sort of move. Instead, we want the behavior to be more physical and sort of limit the acceleration so that the player interacts with the heavy object and moves slowly, or it's not able to push it if it's too heavy. And for lighter objects, it's just able to easily push it out of its way and move ahead. So this is what this max acceleration parameter handles, which sort of limits the force that the controller is going to apply on the player, and that way we have a somewhat realistic behavior. So with that being said, we just add the acceleration, we get the mass multiplied by the acceleration, and we get our force. So this is complete how we handle the motion. So now let's just switch back to Unity and see how do we tune these two parameters and get a player that moves around. Okay, so now we are back to Unity and we'll see two new parameters. So before we start, we want to ensure two things. We want to untake freeze position X, freeze position Z. So before we had frozen the position, so we could check the hovering behavior, but right now we want to move our rigid body in these two axes, so we want to disable them and sort of check how it works out. So we just disable the freezing and then we'll start with the script. So I think a speed of 10 is good enough. Acceleration I'll be just putting 1000 and we'll need to see what. So as you can see, the player can now move around with the arrow keys. It's a bit too fast, but yeah. So with that, we have sort of completed our controller. So now we just have to figure out jumping. So let's just start with the implementation of jump. So for jumping, we need a few parameters. Jump. So this will be the velocity in the y direction, which will be applied to the player when the player wants to jump. Next parameter is to disable hover delay. So this is being done, hovering effect is being disabled, like jumping for a short duration is because when the jumping force is applied and the spin force is active, what will happen is the two forces will act in the opposite direction and this will cancels because the spin force will try to pull the player to the floor, whereas the jump force will sort of pull the player away from the floor. The two will basically cancel and will sort of result in cancelling the jump. So we basically want to disable our hovering effect for short duration. So to handle jumping, handle few things. So first is trigger jump, disable the hovering effect, and the flow to keep time of the duration for which the hovering effect works. So this will start. First, we take input in the update function, since it's good practice to take all user input and update, whereas do the physics updates in the physics update method. So taking the update,
we see a jump button, we just move to the jump button. Now, let's see how we will handle it. So, to handle the jump, we have a function called handle jump. We invoke handle jump before handle spring because we will disable the spring pole before we apply jump force. So, by doing that, we can ensure that the spring force is disabled before the jump force is applied. So, once it gets so with that done, let's move on to the handle jump. So, handle jump, you want to see there's a trigger jump request. If there's a request, you want to housekeeping and reset it. Now we want to acknowledge it. So before we do that, we do two things. First, we have to check if we are in ground. So if it is in ground, then really we can do the jump. So for doing the jump, because we see when the effect, so we set it to true. We reset the timer and we do that too. So since we are applying velocity and this is going to be applied instantaneously instead of using force mode or standard force mode, we are going to be using velocity change because we want to achieve the target velocity instantly. So how do we do that? So do that to the target velocity, that is this 53, 53 run up into jump velocity minus the current velocity of the jump. Then instead of force mode to velocity change, so we also have other modes like impulse, where you just have to multiply with the mass of the rigid body, add force, where you have to divide by the delta time, and do that, but since this is more convenient, you can do that. But the issue over here is you're not bounding the force. Whereas in add force, you may want to bound your force and give it a go against. But for jumping, this is good enough. But you have to improve it. You can use force mode or add force and sort of do the tuning with the fixed delta time and all that. This is overall more pleasant and gives a better experience compared to the standard. So with that being done, we just now want to handle the timer. So this is simple. Now once the timer runs out, we want to reset to the original state. So in spring force, we just have to run the chain and check if disable or set to false, only then apply. So with that being done, let's move on. So to get the jumping effect working, you have to change a few parameters. So first thing that you want to do is reduce your slack height. So the slack height before will be something like 0.1 or 0.2. But now you want to set it to something like 0.9 minus 0.4. So the reason for this negative value is basically since we are doing a sphere cast where the sphere is also coming along, so that adds an extra additional height to the recast, meaning the radius gives an additional margin of error. So we want to sort of reduce that margin of error by 0.4. So we want the recast to only go from the origin of the player to around 1.09. So by doing that, we sort of ensure that when the player is in air, it doesn't get directly pulled to the ground because the slack height is not that large. So if the slack height is very large, then that will cause the player to be directly pulled to the ground while it's in midair because the spring will sort of have its effect, which is basically controlled by the slack height, meaning the distance up to which the sort of spring effect takes its place. So with that being done, one more thing we want to do is we want to reduce our spring force constant since we want to make the jumping or landing a bit more slower and yeah, I mean you have to tune those values and sort of find out the best values. So to get a good experience, I found that these values were better. So let's just set the velocity to 8 and 0. So and the force constant and damping we have experiment. And fine. Now you can see a player jumps, so the jumps are too big, so let's just make them smaller. Now we have smaller jumps, and you can see the player is now able to jump. Let's make it slightly bigger so it can climb. As you can see, the player can now climb up, move up the ramps. So here is where we would move slack and better. Increasing the constant. So now you can see it snaps to the ramp. My speed seems to be a bit fast. It's reduces and controls. Now you can see a jump forwards, up and down, go down the right. Yes, that's just pretty much about it of jump will be implemented. Now we'll sort of go on how to deal with the camera, sort of send the camera into player's viewpoint and then have this mouse control to move and sort of rotate the camera. Now to implement the mouse controls, I have two simple scripts, so I'll just go over them. They're very simple. So we first have two parameters for the sensitivity of the x direction and the y direction of the mouse, and then a global scale factor, which basically used to scale both of them. And then we have another control which is for the maximum and the minimum pitch. So what is pitch? Pitch is basically the vertical movement of the camera, meaning the vertical rotation, whereas yaw is the horizontal rotation for the camera. So the pitch and the yaw are also tracking these two variables, rotation x and rotation y. So if you just have a quick look at the code basically just locks the cursor into the center of the frame, which is done by this one, this line. Then you basically change the rotations based on the mouse movement, and you apply the rotations to the gimbal and the transform. So basically you want to rotate the player in the direction in which the mouse is moved, meaning you want to yaw the player in the correct direction. At the same time, you want to pitch the gimbal, which is the camera, up and down based on the vertical movement of the mouse. And with that, we sort of move the camera. The next script is player camera gimbal follow. So this is basically a script which sort of makes the camera follow the gimbal of the player. So this is being done so that the camera has a smooth effect and it reduces the choppiness which you get if you parent a camera to a rigid body, meaning the camera is a child of a rigid body. So that causes issues because the rigid body gets moved during the fixed update, and whereas the camera renders during the update, so all those cause some amount of jittering. So to remove that, we update the camera's motion in late update, because during the update we calculate the position of the gimbal, and in late update we sort of move our camera to that position. Along with that, I have some dampening in the y direction so as to reduce the effects of the springs bobbing if it's there. So let's just head to Unity and see how do we set this up. So in player we had the FPS mouse controller script, we configure the parameters, and we set gimbal as the gimbal. So gimbal is just basically a child of the player, so this is sort of where the camera will be placed. And for the camera, you just have to add this follow script, set the player as the FPS mouse controller, tune the damp a bit, run. We have our fully working game with the Rigidbody FPS control. As you can see, the controller is quite smooth. Nice jumping interaction, can climb up and down stairs.